So thank you for joining. I'm Hitoshi Murai. I'm in charge of the programming, designing programming environment for FugakuNEXT. Today, I'd like to give you the brief overview of programming environment, current status of investigation of programming environment for FugakuNEXT so far. Okay, this is introduction. First of all, I believe you know very well that FugakuNEXT compute node will consist of Fujitsu X CPUs and NVIDIA GPUs. So therefore, programming models supporting both of these two are needed for you users to achieve good performance on FugakuNEXT. In particular, models for programming GPUs will be essential. Actually, we have not yet had we had less experience about these programming GPUs because Fugaku has no GPUs. It's a pure CPU machine. So this is today's agenda. First, I'll talk about the possible programming models for FugakuNEXT we are investigating. And then our opinion about the comparison of these programming models. And then based on these comparisons, current decision about the basic policy on programming model of FugakuNEXT. And in addition to this, I will explain some two additional related technologies about the programming models of FugakuNEXT. And last, finally, I'll summarize this talk. Sorry. Okay, this is a possible programming models for FugakuNEXT. We have investigated. For first, directive-based one, OpenACC and OpenMP. And second, CUDA. And the third one is the so-called standard language parallelisms, including standard PAR, STD PAR for C++, and do concurrent for Fortran. And finally, portable programming models, such as Cocos and Shiku and so on. But today I will skip the Shiku. I will talk about only Cocos. Okay, first, OpenACC. OpenACC is, directive-based model for heterogeneous computing, essentially GPUs. It's introduced in 2011 by first by Clay, CAPS, NVIDIA, and PGI. But as you might know well, it's currently supported only by NVIDIA. It's the supported language for OpenACC is C, C++, Fortran. This is the very simple, short and simple sample code of OpenACC. In this case, this loop is annotated by this directives to offload these work to the GPUs. Okay, next one is OpenMP. OpenMP is another directive-based API. First, for shared memory parallel programming at the first stage. Yeah. And it's the first specification is released in 19 1997 by a consortium of HPC vendors. And in addition to this, accelerator offloading feature is added from version 4.0 specification. It's released in 2023. You can see the offloading feature of OpenMP is released after around 12 years later than the OpenACC. And the supported language includes C, C++, Fortrans. The point of OpenMP compared to the OpenACC is this OpenMP is supported by every compilers. However, offloading, very generally speaking, offloading in OpenMP often performs worse than OpenACC because compilers are not yet matured. So, because the offloading features of OpenMP is much newer than OpenACC. This is a code example of OpenMP for offloading features. Like OpenACC's, the loop to be offloaded to GPUs are annotated OpenMP OMP directives like this. Okay, next one is CUDA. CUDA is NVIDIA's parallel computing platform, platform and API for programming GPUs directories. You know, CUDA is NVIDIA's proprietary product. It's released in 2007 by, of course, NVIDIA, enabling general purpose GPU computing, GPU, yeah. The supported languages C, C++, Fortran, and Python by so-called PyCUDA and number. And there are others. Other support. There is a support for other programming models by bindings. This is sample code of CUDA to be offloaded to GPUs. Okay. Next one is so-called standard language parallelism. It's a standard syntax. Standard means syntax in the language usual language standard. Standard syntax to assert parallelism of a loop, including std_par supported since C++17, and do concurrent statement supported since Fortran 2008. Now, with this syntax, the compilers can parallelize or offload the loop for themselves. These two are the sample code for std_par and do concurrent. Note that it might not perform well because these features, these syntax, assert no additional information other than parallelism. I mean, these syntax provide no information about such as data movement between CPU memory and GPU memories and so on. It only gives the information about parallels. Okay, and next is COCOS. COCOS is an open source C++ library for performance portability across CPUs, GPUs, and accelerators. It was developed by San Diego National Laboratories starting around 2012 in the exascale computing project ECP. And one remark is COCOS is recently adopted by CEA in France, also CEA in France. And the point is, actually, many applications developed in ECP, exascale computing project, are already implemented with COCOS. And so, I mean, there are many users in the US, many users of COCOS in US. And dedicated tools such as a profiler and debugger and mathematical libraries are available and maintained in the user community of COCOS. And I mentioned COCOS as a portable programming models, and its portability depends on available multiple backends, such as OpenMP, CUDA, SHIKU, and HEAP, and so on. I mean, this is a sample code of COCOS, and in this case, this loop, this work is offloaded to GPUs based on the one of OpenMP, CUDA, and SHIKU, and HEAP, and so on. With a selection of users. And please note that now this COCOS is one of the projects of High Performance Software Foundation. HPSF. HPSF is established last year, and now under the Linux Foundations. Okay, and this is a comparison. Please note that this is our opinion about the comparison of these programming models. Okay, first for performance, CUDA is of course the best, and OpenCC is the second. And in our opinions, OpenMP is still not good, and standard language is not so good. And COCOS is in this case I like the triangle marks. It means the performance of COCOS depends on the backends. And note that the performance of OpenMP should improve if compilers matures in the future. This is the current situation. For easiness of programming, the standard language parallelism is best because, of course, because it's only it uses only standard syntax. And I marked good for OpenCC and OpenMP because they are directive based. And CUDA is if you using CUDA, you have to modify your source code. So it's not good. And the Cocos is also need modifications of your source code. But yeah, in my opinion, Cocos is so. And for portabilities, in this case, standard language parallelism and the Cocos are good. And OpenMP are good in a sense of that every compiler support this. And OpenCC is triangle mark. It means in effect, OpenCC is currently only supported by NVIDIA. But OpenCC, the standard of OpenCC is a standard, so not a proprietary one. And CUDA is a proprietary one, so it's the portability is not bad. In other words, there is a point of concern that so-called vendor lock-in is a point of concerns for OpenCC and CUDA. Okay, based on these comparisons, we have almost decided about the basic policy on programming model for FugakuNEXT. First of all, OpenACC is a central means for offloading on FugakuNEXT. Second, we recommend Cocos to users, in particular for brand new C and C++ projects, and possibly for brand new Fortran projects, because a tool for Cocos Fortran interoperability will be provided by us, RIKEN. And it can be expected that the NVIDIA and Fujitsu compilers support OpenMP, CUDA, and standard language parallelism for themselves. So you can use these programming models with NVIDIA and Fujitsu compilers. Finally, others, such as SQL, should also be available as external or open source package. Okay, so in these some slides, I will explain. I'd like to explain these tools for Cocos Fortran, but I will explain it very briefly. With these tools, a user does insert a directive before the target loop in the Fortran code, and add initialization, finalization in the main program. Then the tool does translate the Fortran code and generate a Cocos code for the annotated loop, and generate the Fortran module to define interfaces of this Cocos code. Like this, you have this code, and this is just examples. You insert the directive for the target loop, and then the tool automatically first the tool automatically translate this target Fortran code like this. I mean, in this case, the loop is replaced with the invocation of Cocos Cocos functions. And Cocos, the tool also generates this Cocos code. In this case, here, the Cocos function corresponding to this loop is here. And then the interface Fortran code to define the interface of this Cocos functions. Okay. And so far, I talked about the currently decided basic policy on programming model for Fugaku NEXT. And in addition to this, we are investigating some additional technologies about the programming models. The first one is the conversion between OpenMP and OpenACC. Actually, there is some tools which support the conversion from OpenMP to OpenACC and or vice versa. First one is CLAC, developed by Oak Ridge National Laboratories, which translates OpenACC to OpenMP for C or C++. And the second one is Intel's application migration tool for OpenACC to OpenMP API, which is for C++, Fortran. Yeah, this one supports Fortran. So finally, ACC to OMP for Fortran, developed by University of Illinois. Actually, now our GPU vendor is NVIDIA. So OpenACC is the central means for flooding. But before the vendors, GPU vendors fixed, we are considering to another situations where OpenMP is the central means. So in such cases, these tools are more important. But in the current situations, the priority lowers. However, we can consider there is some cases these tools are useful. And in addition to this, these Solomon, which is developed by University of Tokyo. Solomon is a unified directive to be substituted to OpenACC or OpenMP1 with a selection of users. This is a sample case. This offload is the unified directives of Solomon. In this case, with a selection option specified according to the option specified by users. This offload Solomon directive is can be substituted or translated to these OpenACC ones or OpenMP ones like this. It's we think it's very useful on Fugaku NEXT, and we are considering to support this. And the second one is Jack. So Julia accelerated. First, Jack is a Julia library for a unified front end on top of multiple backends. So yeah, just like Cocos. And Julia is a high-level, high-performance programming language designed for numerical computing, data science, and scientific applications. It's first released in 2012, and now official version 1.0 released in 2018. You can see the Julia code is very simple, just like similar to Fortran or C. I mean, the syntax of Julia itself is not so special, but there are some remarkable characteristics like this. It's dynamically typed, and JIT compile. It has a JIT compiled features via LLVM, and it combines ease of Python, R with speed close to C or Fortran. And there is a very rich ecosystem for machine learning and scientific computing and parallelism. We are very interested in Jack to be supported in FugakuNEXT, and now we are starting to investigate Julia and or Jack. Okay. Now I summarize my presentations. First, 4 programming models on FugakuNEXT. First, OpenACC is a central means for offloading. And second, Cocos is also recommended, particularly for brand new C++ projects. And we are developing a tool for Cocos Fortran interoperabilities. And in addition, we are studying additional technologies, including conversion between OpenMP and OpenACC, and Jack such as Jack that is Julia accelerated. Okay, thank you for your attention.